yeah, something else written in the program, but it's about light technology, LED technology, current and near future possibilities. Please.
Morning, everyone. It's very nice to be in Drammen. I hope you'll forgive me for not knowing Norwegian, and you'll be able to suffer through American English. I want to thank really our host, Arne Stensvand, who's here to host us, but David Godoy from Cornell is really the person that made my colleague Mariana Figueroa, if you want to wave your hand there, possible. So we're starting a collaborative project, and I guess I was drafted to give a presentation, which I'm, as a professor, always happy to do. I thought with David's advice, I would give you just a little background of who we are, because probably most of you haven't heard of us. We're at a university in Troy, New York. Not New York City is often confused, but we're actually in a historic building of 30,000 square feet. And it's largely an open warehouse that we have converted into a laboratory. What makes us a little different than most universities is that we're running about 50 projects at any one time. We have a throughput of about $6 million a year in R&D. We also teach and do research. So we're an interdisciplinary center working with lighting. And some of the programs that we're involved in, we do everything from transportation. For example, we do all the lighting for the Federal Aviation Administration. We're very much involved in daylighting, architectural lighting design, outreach education, so I encourage you to check our website every once in a while if you want to learn a little bit about lighting technologies and so on. We have an energy center in Sri Lanka. We do work in the Philippines, so we're very global. One of the areas that we're involved in is light and health. How does light impact the human circadian system? That's a cross-section of the Boeing 787 Dreamliner. We did the lighting design and application for that with the goal of trying to make first-class passengers arrive at their destination a little more rested. What I'm going to talk more about probably is the independent testing. We're the largest university devoted to measuring light and electricity. In fact, that is really sort of our core activity. So we do all the support for the U.S. Department of Energy, the Canadian government, all through our photometric testing, radiometric testing laboratories. So at least we think we understand the physics of optical radiation well enough to be able to quantify how much is delivered, and we develop measurement systems and standard test methods to do that. Now, this is sort of an abstract diagram, but this is mostly what we work on is the human condition. And so there's sort of two major systems in the human transduction of optical radiation neural signals. The blue line is the sort of what we've known for several hundred years now is the visual system. And then the green one represents the neural pathways from the eye to the pineal gland, which is the center of the brain that generates melatonin. And so it's a very circuitous road, goes down through the superior cervical ganglion, back up into the brain, and so on. But the reason why I'm showing this way is at the center of what we're involved in, whether it's for Boeing or it's for the Federal Aviation Administration or transportation, you want to have productivity, health at the core. And the way you're going to convert optical radiation, you have to go through the visual system and the circadian system. And the way we systematically look at both of these systems is the amount of spectrum, distribution, timing, and duration. You could add polarization, but that's a rare interest. But you can actually systematically approach these problems by really decomposing light into these components. And so if you take a sagittal section through a head of cabbage, we see an analogy here that you can also break light up into amount spectrum distribution for a different sort of phototransduction mechanism. And you have photosynthesis, which is reasonably well understood, but the photomorphogenesis, in my opinion, is going to be where the opportunities lie as you match the solid-state lighting technology with this phototransduction mechanism to do things like change the nutritional value, as well as the appearance and so on. So we've heard about that in the last couple days. Now, if we start with amount, On the left is other colleagues at Cornell University showing that for a given year, you can get practically anything in a greenhouse, anything from high light levels, which is too much radiation, to too low. And so there's a real opportunity to begin to think about lighting controls in that kind of application. And here's data from them showing that after 35 days, dry weight lettuce, it's nearly proportional, not perfectly, but nearly proportional to the optical radiation. Some have concluded, for example, that it doesn't really matter anything else, just dump photons on lettuce and it'll grow and you don't have a problem. It's a little more sophisticated like that, as I'm sure you know. The other sort of myth, I guess, that I hear sometimes is that we're always trying to emulate natural light. But the electric light you see here, whether it's high-pressure sodium in the terms of spectrum or new solid-state LEDs, is quite a bit different than what you're going to get with natural solar radiation. So you need a systematic way to understand what the photopigments are in a material. And then you would ideally want to begin to match the spectral output with the sensitivity of those photopigments so that you can systematically manipulate it. Arguably, you want to get as far away from natural light as you possibly can to begin to steer what sort of outcomes you want from plants. But you basically start with this palette where you have the spectral power distribution and the photopigments is best understood so that you can begin to orchestrate how you want your plant to develop. Now, to kind of give you a frame of reference, the black line here, black function is your standard measurement of light. So if you take a traditional light meter, it will be calibrated in terms of what's called the photopic luminous efficiency function with a peak sensitivity at 555 nanometers. It actually only characterizes 2 of the photopigments in the human retina. There's actually 5. And that pink line, or whatever color that is, magenta, is really sort of the bandwidth that human eye is sensitive to. So it's much broader than even what the light meter reads. But remarkably, to me anyway, is if you look at your classic McCree function from 1972, plants are even broader than that. They extend into the infrared and the ultraviolet. So plants really have a much broader acceptance angle, if you will, of optical radiation than even the broadest that humans have. Now, what's important is then taking a function like this and being able to tune this high-pressure sodium, which is the standard light source that you're going to use for greenhouses. Here is a particular white LED. This is with a blue emitting radiation from a blue LED plus the white phosphor. And here is a warm white phosphor. And I'm surprised, I guess my question is, I always feel that the white LEDs are not often used in growing. That's my impression. Is that true? They're usually narrow band spectra. But if you do your sums, it's not a bad light source, and these are common now and reasonably inexpensive. So an open question, I hope somebody will give me an answer. Why are these sources not more widely used for agricultural applications? Spatial distribution is one of the areas that I think people have thought about amount and spectrum quite a lot. But you're seeing now people dropping light sources down into the foliage to activate the plant, and there's some very interesting ways to begin to think about that. We heard yesterday about these colored nets out of Israel, which I think are very interesting in being able to mitigate solar radiation, but also shift the spectrum so you can differentially affect the flowering and the fruiting from the different plants. So there's a lot of interesting opportunities there. But what seems to be the general case, and this is just one graph out of the literature that shows that diffuse radiation is actually better for efficacy, if you will, than just downlights that sit over the top of the plant. So the idea is, are there creative ways we begin to think about new optical distributions in the greenhouse other than the ones we've normally considered? Now, some have argued that intermittent light is more efficacious for plant growth. I think the evidence is fairly clear that's not true from the work that Sager's done way back, but that still pops up as a possibility. But it does seem that it's the integrated energy, time, and amount that over the spectral range that you're interested in that matters. But There's some interesting new data out of Japan. I'll explain the one on the left and then the one on the right is that if you run an LED with direct current, that means it's on all the time, and your average is 20 micromoles over that period of time. If you do what's called pulse width modulation, that's what PWM means, you're actually modulating the light. At the same amount, you get pretty much the same yield. And that's with a red and a blue LED. But what's very interesting is that if you counterphase the red and the blue, you attenuate the growth, and that's what's shown here. So you have the same amount of radiation, you have blue and red in phase, as opposed to out of phase, and the plant can respond at, you'll see here, 2.5 kilohertz, which is very fast. So there does seem to be a little bit more to the story of total energy. You also have to think the phase relationship about the optical radiation. And as you get into solid-state lighting, for high-pressure sodium it doesn't matter, but for solid-state lighting where you have multiple sources, these kinds of issues can become interesting and may also have some practical applications. Now, you know a lot more than I do about photoperiod, flowering in particular. But one of the things that I've not seen much in the literature is, and the thing I'm actually sensitive to right now, is jet lag. Are there ways that you could take the same light-dark interval and begin to shift it suddenly so that, for example, you could differentially affect, say, a pest as opposed to the plant itself? So is it possible to give a pest jet lag and have some benefit by simply changing the light interval? And then, of course, these are sort of classic studies in circadian rhythms in mammals where you have a free-running period. So the plant never entrains to any light-dark cycle. Those can be quite detrimental to humans. The question is, what are the outcomes for plants? So I think there's a lot of opportunity beyond just amount and spectrum, where you begin to think about spatial distribution, the temporal domain, to begin to think about ways to use energy efficiently and at the same time shape the outcome of that plant. Again, very different than what we consider to be natural lighting conditions. Now we're going to intersect some of the work that we're actually involved in right here. One of the things that is of growing interest in the United States is how do we define efficacy for a plant application? So as we see a growth in the use of high tunnels and greenhouses, the question is, how do I measure how effective per watt a light source is going to be? And so it actually has implications for policy in the United States, economics, and so on. So this is a project we're doing for the Natural Resources Canada. They're involved in basically quantifying the efficacy or effectiveness of different light sources for these applications. Our laboratory is really state-of-the-art with regard to being able to measure light, and I'll show you next the kind of data we get out of our laboratory. So we use an RGB imaging photometer, and this then represents the spatial distribution. This is your sort of classic high-pressure sodium, and this is going to tell you your YPF as a function of area. And why do you care about that? Well, because if you're going to lay out a greenhouse, you want to make sure that you have matched the next one so that your peaks and valleys are flattened out. So you don't want just a dark spot. So you have to optimize the spacing. The other thing I think it's important, based on the talk I heard yesterday, most people stop here for recording the optical radiation, but what you'll notice is a huge high infrared spike in high-pressure sodium. So if you're going to just simply quantify YPF or PPF, for example, you're forgetting the long wavelength radiation. So the heat will increase considerably for the same measured optical radiation. This is the spatial distribution on 2 axes. So this sort of gives you the distribution, the intensity distribution coming out of it. And this chart here is a sort of a plan view of your red-blue ratio. So we're able to look at the near and far end of the spectrum to quantify, is it uniform or not? And what's graphically shown here is high-pressure sodium is uniform. Those ratios are very close to a fixed amount no matter where you are. But if you now go to an LED, the first thing you notice, it flattens out a little bit. The color changes by the spectrum. The distribution's different. And all of these pieces of information become very important as you begin to compare one system to another. So you can see the optical distribution of this LED system is very much different than the previous one, and again, very different than HPS. What's important, though, as you go through these, is you begin to see that there are differences. This particular one, you'll notice that the red and the blue peaks are not spatially aligned. So one plant's going to get a lot more short wavelength, and the one next to it might get more long wavelength radiation. You need to know this to be able to explain what the outcome is. And you'll notice, too, that it's not a symmetric distribution. So the plants on one side are going to get a lot more than the ones on the other. If you don't know that, you have a mystery on your hands with regard to the application of lighting. So these become the raw materials for the kinds of things that utilities and governments are interested in. What we have here is the price for those systems I just showed you, the YPF generated, and then the efficacy. And I'll start with the efficacy. The LED here has the greatest YPF of any of the light sources, but you'll notice that it has less optical radiation, and it's going to be more expensive than the high-pressure sodium. So don't think of a single number, whether it's price or it's how much efficacy you have. You have to think in all three of those dimensions to make the right selection and the right layout in a greenhouse. But again, these are the kinds of things that, at least from my perspective in the United States, these are not mainstream. They are in sort of when you deal with human effectiveness of light, but this is sort of an emerging area, from my perspective, in the United States. I'd very much like to get your feedback. Now, in the United States, lumens per watt sort of drives everything, and that's sort of what they're forcing it to in terms of quantifying how effective the light sources are for greenhouses. But I don't need to tell you much about photomorphogenesis. Depending on how you balance that spectrum, you can get quite different outcomes of the flowering and the shape of the plant and so on. And that is a question unasked in the United States right now with regard to policy. So these are important additional issues that I think, because these photopigments make a big difference, as we've seen, in how you're going to combine, in this case, short wavelength radiation. The point I want to make here is that we now are able to take a spreadsheet that we have and be able to quantify not only the YPF, but the photomorphogenesis, provide you a cost analysis, be able to make an economic determination about what at least the calculations tell you. Should you use a warm white LED? Does that make sense? What's its optical distribution? What's the spacing? And so on. Those things are interesting in and of themselves, but in the end, you've got to put it in a real greenhouse. And what we found is there's nothing really fairly sophisticated with regard to laying out both the natural and the electric light that you're going to get in a greenhouse. These are complex structures. They have large glass surfaces, which most architectural lighting software doesn't handle. And then, of course, you're dealing with plants, not with people. So you have a different optical or spectral sensitivity on your hands. You also have to think about shading. One of the real fears that you get is if you get a big fixture, you've now attenuated natural radiation. So the profile also becomes important in all of your considerations. The integration of electric and daylight is, I think, a huge opportunity, and now the tools, at least from our laboratory, are available to do that. But what we've done is leveraged what has been developed since the early 1980s. This is AGI 32 renderings of, this is an architectural space. And what you're interested in this application is how does the space look? Where is the light distributed? This is a false color representation. You can change in virtual what your layout's going to be. And you can do that for any space now. And this is pretty much mainstream way to do architectural lighting for humans. That is what we've tried to adapt and compare to, as far as we know, virtual grower. Are you familiar with virtual grower software, which is, at least in the United States, the USDA has produced it to try to give people anywhere in the United States what is the natural radiation that might fall in your greenhouse. And so what we wanted to do is compare that with this software that we modified from architectural applications. And it's good to a first approximation, but when you really get into complicated structures, This is a greenhouse on an old factory in Brooklyn. Urban greenhouses are becoming more and more popular. Shading becomes an issue. This is a water tank up here, so how's that going to affect the growth of my plants? What color the wall is also matters considerably in how much radiation you're going to get. So we tend to think of greenhouses out in the middle of nowhere, but in fact, these are becoming more and more popular, and there's a lot of government funding going into these. You do not have the software able to generate these kinds of spaces, very complicated spaces, and then be able to quantify, for example, how much radiation is falling on these during overcast days, and you see October, December, and February, and then you've got direct or clear skies during the different seasons as well. So being able to have that and then be able to calculate or measure how much optical radiation have on individual tables. This bar here represents how much is on the roof of the greenhouse, but you can look at different locations within the greenhouse now, taking into account the structural characteristics, taking into account the shading from the light source to be able to then optimize when the shadows begin to curve, to be able to rebalance the light in different ways. So we're kind of leveraging what we know about architectural lighting applications and applying them really for the first time in greenhouses. So we think this is going to be sort of a wave of the future. We're seeing much more interest in, I've used growing 3 times in this, growing interest in growing plants to extend growing season. This is the kind of mindset that we're seeing now evolving in the United States with regard to policymakers and utilities. The integration of daylight and electric light is a concern, but no one, to my knowledge, has a real practical solution to that. The growers I've talked to trust the manufacturers to tell them that, and then they end up somewhat disappointed sometimes. Naturally, they're in the business of selling you hardware, and they will do calculations, but you really don't have a good way to verify it until actually it's installed. I think we can do much better than that. I think the mindset in the regulators is the maximum yield at the lowest cost, which makes sense. Minimizing pests, they understand those kinds of issues, but they really don't have any of the policy tools in place to actually do anything about it. So I see an evolving decade of education, at least in the United States, for policymakers to help support extended growing seasons. And energy efficiency is really a central concern to the utilities because their bottom line is affected by how effective or efficient that the light sources are. And they're a little bit lost now with regard to the growing use of electric lighting in greenhouses in particular. And so they're looking to us at least to help them sort through those policy decisions. I can't tell you how supportive I am of solid state lighting. I think it has huge potential, but I've put potential in italics. It's higher cost right now, and you really don't have the computational tools, in my opinion, to be able to justify moving away from high pressure sodium to something risky. You saw some of those data, and some of you are going to get burned, not the plants necessarily, but you're going to be disappointed if you simply look at how much flux is coming out or whatever. It takes a much more sophisticated level to really lay out a greenhouse. So all I can say is be careful when you do that. But I think the real potential is what I call a new value proposition. It isn't about dry weight. It's about the taste, nutrition, medicinal value that you can extract from these plants that get your numerator higher on that value proposition because people will pay more for those kinds of things if they feel that it's healthier or better for them and so on. And then I think sometimes it's forgotten about you can shape a plant to optimize things like shipping or displaying in a grocery store, for example. You can actually shape the plant to be what you want to fit the machinery rather than the other way around. So I think there's just really exciting scientific and practical potential for this area. And I do think that we're at the front end of the wave, at least I'm giving you the United States perspective, I think, where now you have a lighting technology with a great deal of potential, but you need the tools to make sure that you can harness that potential, and you're seeing a growing interest amongst public policy in the United States that I think that's going to converge. I don't know what the European experience is, but I'm hoping that we have enough time that I can hear from you rather than you hear from me. So I thank you very much. Some of our sponsors, our colleagues, I've already acknowledged Mariana Figueroa, who's in the audience, but we've got a lot of talented people in our laboratory, and if you're interested, you can go to our website with your smartphone by taking a picture. So thank you. I appreciate the opportunity.
Thank you very much for an interesting talk. I'm sure there will be some questions for you.
Well, or lectures to me. I'm happy to be lectured at as well. I'm here to learn.
Hello. Concerning your question that how much white LEDs are used in horticulture, and one thought about these, well, LEDs in general, if you use only these white LEDs, you're missing the far red part. So by using those, you can't control the photomorphogenetic responses. So, yeah, basically, and with only red and blue LEDs, you can go only so far. So you need a bit sort of different kind of solutions for different purposes. So there's no one like gem stone to fix it all.
But is it true that still sodium is the primary source in greenhouses?
Yes.
And so...
sorry, I have to have a microphone.
If you... Can you hear me all right? If you want to move from sodium, what do you do? I mean, do you have computational tools that allow you to, say, supplement it with far red radiation? Or how is it that you proceed if you want to move to modern technology? How is that really done here?
Yeah, well, that's a good question. If you think of, like we heard yesterday from Tom Dweck, that if you take this interlighting concept, for example, and with cucumbers and tomatoes, and that are considered quite low-value crops, there the payback times can be so long that there's just no point. Then there's one growing direction that is hybrid lighting, that you sort of supplement your high-pressure sodium, because high-pressure sodium lacks the blue wavelengths, and that can be really problematic during the winter times especially. So that's one option. Then there are, of course, these situations when you have no natural light at all, so and where high-pressure sodium is just not practical because you can't put it close to plants. So there are so many options, so it's very situation dependent.
Well, when it comes to engineering, you rely on the manufacturer to engineer a solution for you? Is that how you do it?
Mark, I think if you want to look for a solution for horticulture, you first look at your plant. What does your plant want? You can make almost anything with your technology, but you have to know what your plant needs. And so what we've often done, if we've done in the past, is we've been given a technology and we've seen, does it work? And often, like we just heard with interlighting, it doesn't work in the way that we thought it might. So then we're not looking at the plant enough to see what it needs. And so I think that's where you have to start, to see what your plant needs, where it needs the light, what kind of light it needs, how much, when, and then apply it.
Well, we have the same problem with humans. They're all different as well.
Is it a problem?
Well, it can be, but it is, to your point, diagnosing. Yeah. But I drew a slightly different inference from your talk yesterday. When you showed the chrysanthemums,
yeah,
the relative contribution of the far red was the same, even though the absolute was different for the different varietals, I thought. Yeah. So what I saw in your talk was you can extract general principles. Obviously, you were going to have different applications for different ones, but the general principles were the same. Was that the wrong inference to draw?
No, it's right, except there are other, to my way of thinking, in horticulture, light is your most important factor, but it's not the only one. And,
absolutely. That's all I know, though.
Right. But it's, I look at it as a light climate within with integration of light, temperature, relative humidity, and a number of other factors. So we try and integrate them to let the plant grow as best as it can. You were just mentioning something about natural light and artificial light. again, what we've done the last few years is look at the plant, how much light it needs at different stages of its growth, and only use artificial light when necessary. Use as much natural light as possible, and phase in your artificial light as you need it. And no, that's another way of looking at the climate, the light climate your plant needs.
Yeah, and that same principle applies too, that people are concerned with new fixtures that have large profiles that begin to start to shade the plant. And
yeah.
So those kinds of issues, I agree that when the lights are off, you can also impact how much natural light's going to be on the plants as well.
Yeah.
So
we consider that HPS lighting blocks out about 3% of natural light in a greenhouse, and the LED fixtures that we use, they go up to about 7% blockage, which is, if you're looking at about at least the ones that we use, but if you're looking at the general principle that 1% of light means 1% less or more production, then you're losing a lot just by not watching out with how large your fixtures are.
No, all those things I agree.
Yeah.
But again, let me come back to my first question. I just would like to take at least one thought away from me. Is it true that the growers rely on the manufacturers to do the layouts of the lighting, the spacing and the amount, the wattage and everything else? Is that generally what it's done?
Yeah, they make light plans to make a uniform light distribution at the canopy level, and there are, I suppose, a number of computer programs that do that, and they rely on the growers for that. And the suppliers, the light suppliers, they always go for a plus. They never make it just what's required. They always put in some more light.
Okay.
Play safe. Yeah.
Well, if I could just say one word, I don't want to overrun, but what's really interesting about this is if you have a sophisticated eye, the LED systems are trying to emulate, if you will, high pressure sodium. But what we found in things like parking lot lighting is that solid state lighting, because you can sort of orient each of those elements separately, you can have a very flat pancake of light, which would be ideal for a greenhouse that you can't get with sodium, for example. So being able to think about the next generation, the potential, and having those tools at hand, I think is where I think it's going to go. And I think solid state lighting will displace sodium, despite you saw the costs and all the other things. I think we have the potential here to do it, and the individual control, I think, for photomorphogenesis, I think is really a powerful potential. And I think you made that same point yesterday. Anyway, I'm sorry I rambled, but I was hoping to hear more. So thank you very much.
Thank you very much.